Thank you very much. So the third talk in session 4 will be given by Iskender Yalcinkaya from the Czech Technical University in Prague, which is actually serves also as the center for the Q-Czech organization, which is one of the Q cousins organizations of QWorld. And the topic, we are going to continue the topics of quantum walks, and you are going to talk about disorder-free localizations in quantum walks. So thanks a lot, Iskender, and
thank you.
Very interested in this. Nice
thank you, Zoltan, for your nice introduction. So I don't need to introduce myself. Today I'm going to talk about one of the recent publications of ours. With the title Disorder-Free Localization in Quantum Walks. So Stacey already told us about quantum walks, and I'll introduce you what do we mean by disorder-free localization in this context. So localization always manifests itself in some type of disorder in the spatial or temporal degrees of freedom. For example, in the Anderson's seminal work, if you write down an Hamiltonian like this, maybe I better switch to. If you write down an Hamiltonian like this with only hopping terms, as we see right here, without, I mean, if W is 0, and if you look at the eigenstates of this Hamiltonian, they are nothing but Bloch states. So a quantum particle with only hopping terms in its Hamiltonian is able to spread along the lattice freely. But if we introduce some on-site irregularities, disorder in this Hamiltonian, which I mean that if W is not 0, so the eigenstates are represented by this recursion relation. So this recursion relation can be solved by a transfer matrix method, and in the end we will see that all eigenstates are exponentially localized. So if we have a disorder, if we have some random potentials for on-site energies. So what is disorder-free localization in this manner? In 2017, these scientists introduced this concept, actually. It's in their own words, actually, a completely transitionally invariant quantum system can generate its own randomness dynamically via extensive set of conserved quantities, which leads to localization in one of its subsystems. Actually, it's an excerpt from the abstract of this paper. So we don't need to introduce any disorder, any spatial disorder in our system, and we can start with a completely homogeneous initial state. Even in this case, because of the interaction between the degrees of freedoms of the system, the system can generate somehow its own randomness. I'll explain it later in our model, so I'm not going to go into the very details of this paper. But what do they have in their paper is they have a bipartite system, and they have spinless fermions and spins, and they interact with each other. And because of this interaction, somehow they obtain in the end a localization in the fermionic degrees of freedom in their systems. So actually, we took this idea from their paper, and we applied this to quantum walks, because quantum walks are more, they are simpler systems compared to this system. So what do I mean by quantum walk? By a quantum walk is a bipartite quantum system, which consists a coin degree of freedom and a position degree of freedom, so that it's actually a quantum counterpart of quantum classical random walks. And this concept was introduced almost 30 years ago by Aharonov, Davidovich, and Zaguri. So that in quantum walk, we also, as in classical walk case, random walk case, we toss a coin first, and we move our particle, walker, according to the coin state. So here, if coin state, for example, is up, if the coin is a two-dimensional quantum system, if it's up, the Walker moves right. If it's down, for example, the Walker moves left. Since this is a coherent process, if we completely start with a localized state in the origin, it spreads along the lattice coherently. The quantum Walker coherently spreads along the lattice. So what is interesting about this is actually, we know that in classical random walk spreads diffusively in the spatial degree of freedom. But a quantum walk spreads ballistically, which is quadratically faster than the classical random walk. Actually, in search algorithms, we can take advantage of this property because it spreads faster than classical random walk. And somehow, if we have a mark state in a given position in a given graph, we can find it somehow quadratically faster than a classical random walk could do. So how do we introduce disorder in quantum walk case? Actually, it's very similar to the Anderson's paper. We introduce a static disorder along the position space, which resembles a spatial random potential for the quantum Walker, as in Anderson's paper, like this. Because in here we had some on-site randomness, we had a randomness in on-site energies of the particle. Now we imitate this this thing, and with kind of other type of spatial randomness. And also in quantum walk case, this kind of randomness leads to a dynamical localization. For example, we can introduce random coin operators for different positions. We can apply the ordinary coin operator first, and we can extend this coin operator with this matrix here, which introduce some randomness for each position space for each site. The other way, another similar way, is actually introducing some random phases for different positions. Actually, these two are almost the same. For example, whenever the Walker steps on this position, it acquires a phase of this, for example. Whenever it steps on this position, it acquires a phase of this. And these phi's are chosen randomly from a uniform distribution, as I wrote down here. So this randomness introduce a disorder landscape for the quantum Walker. And in the end, all the eigenstates of quantum Walker in position space are exponentially localized. A specific case of this this randomness, we can just introduce a single static disorder, for example, in the origin. And in this case, we don't obtain a complete localization. So we can't obtain a complete localization, but only some of the eigenstates of the quantum Walker are localized because of this impurity introduced here. And these are called actually bound states. If we have a single impurity, for example, in our origin, only some of the eigenstates of the quantum Walker are localized. Because of this, and we have actually showed this in this paper we published a couple of years ago. So what do we have in our model? Actually, our model can be understood in a way that which is an generalization of this previous work we did here. So first, let me introduce how our model works. We have again, we have a quantum Walker, but we extend its Hilbert space with a spin chain, like here, like you can see here. So we still toss a coin, and then we still move our quantum Walker according to coin states. But what we do more is actually we introduce the interaction between the quantum Walker and the spin chain, so that whenever whenever the quantum Walker encounters one of these spins in the position space, it rotates them with this amount. And we just call it for fun interaction parameter. So as we increase the interaction parameter, the quantum Walker rotates the spin more. And because of this conditional interaction, actually the spin degrees of freedom and position degrees of freedom are entangled each other. I mean, as the position, this move operator, this shift operator does. I mean, shift operator, you can see here, shift operator changes the position of the particle according to the coin state. So it entangles the coin degree of freedom and position degree of freedom. Similar to that, our interaction operator here changes how we rotate. Actually, it alters the spin chain degree of freedom according to the position state. So it entangles the positions degree of freedom and the spin chain degree of freedom. So let me first tell you about the results, then I'll tell you why do we obtain these results. So this is the energy spectrum of the quantum Walker. Here we have the energies or eigenstates, and this is the interaction parameter, and this color reflects the inverse participation ratio. It's a measure. If it's 1, it reflects that our quantum Walker is spread uniformly along the lattice, throughout the lattice. If it's 0, it's only localized on a single site. And we can see that as we increase the interaction parameter, after some value, all the eigenstates of our quantum Walker are localized. And we can also see this from this graph. Here, this is the probability distribution of the quantum Walker. These are the positions, and this is the probability. The blue reflects the ordinary quantum walk. So our interaction parameter is 0. As we increase it, first we start to obtain some central peaks and also some ballistically spreading tails. But after this value, 1/4, and all eigenstates of the quantum Walker are localized, so it's completely unable to spread in the lattice. So this colored triangle here reflects that actually this upper edge reflects the ballistic spread, because this vertical axis is the variance of the probability distribution, and this is this number of steps. So the upper edge of this triangle reflects a ballistic spread, and the lower edge reflects a diffusive spread. So as we increase the interaction parameter, first, if it's 0, the quantum Walker spreads ballistically, I mean, as we expect. And as we increase it, its spreading rate is decreased gradually. After actually after this value, it's completely unable to spread along the lattice, so it stays put regardless how much we increase the number of steps. And so this is an inverse. This figure reflects the inverse participation ratio of the quantum Walker with respect to the interaction parameter. We can still see here. I mean, after this value, I mean, all the inverse participation ratio is saturated here like that, regardless of the interaction parameter. We have a similar behavior for the variance. So why do we obtain something like this? I introduced this model as a generalization of this one, the single impurity one, because let me remind you one more time. I mean, if we have a single impurity, if we introduce a static phase at a given particular point to our quantum Walker, you obtain some bound states. Only a couple of the eigenstates are localized. So what is different in this new model? So first of all, this is the step operator of our quantum walker. This evolves our quantum walker. And this operator is actually invariant under spin flips, which means that actually this evolution, this step operator commutes with this xn. This is Pauli X operator. It doesn't matter which spin we flip. I mean, this operation commutes with step operator. I mean, the step of this our quantum walker. And if we have this property here, then it means that we have unconserved local quantities in our system. So what does this mean? So for example, we can write the spin states, the spin chain in this way, in Pauli Z bases or Pauli X bases. Actually, there's a confusion here. I made a mistake, I think. And this eigen basis actually is a simultaneous eigen. It introduces a simultaneous eigenket for both the step operator and this spin flips. So if we consider this base actually block diagonalize the step operator in a way that each block actually evolves the system on its own. I mean, if we start with a, for example, coin state like this, and if we start with a localized quantum walker, and let's assume that our spin chain consists of spins initially, which are they're all up. We can write the same state in Pauli X bases for the spin chain. And actually, you can see that here we have 2 to the n possible spin sectors superposed in a superposed state. Whenever this evolution operator acts on this initial state, it evolves each sectors on its own. So that, for example, this sector is evolved on its own. So we have plus, I mean, for all spins. And it doesn't introduce any disorder for our system. But consider the second one, for example, we have plus plus plus, but at the minus. So this minus actually introduces an extra phase for that given position, as we did in this paper. And in total, of course, we have 2 to the n spin sectors. And if we want to calculate the probability distribution of the quantum walker, you can see that we actually average over all possible spin sectors in the end. And which means actually, I mean, we considered all possible disorders which could be introduced, disorder landscapes which could be introduced in this system in this way. All in all, in total, I mean, we end up with a localized, an exponentially localized probability distribution, as we see in this slide here. So actually, we had a lot in this paper, but I want to summarize it since I have a limited time. And I don't know how many minutes have left.
3 more minutes, because we started 3 more minutes later. If you
yeah, I mean, that's all I want to say. It's better to, I mean, these are my collaborators in this work, and you can see what I told you about here in this paper, and more. And if you're interested.
Someone asked for thank you very much for this a nice talk, first of all, but exactly about the paper, someone wanted to have a link. I guess you can just link it in Discord, right? That's the best thing.
Sure.
Iskender, I mean, I think it's very clear. Thank you for this very nice talk. Are there any questions? Okay, I haven't seen any, and neither on Discord at this question, except for the link for the paper. So let me ask you. So I mean, so this type of localization of the quantum walks are they really like in almost like, are they really similar than in the spin chains? So what I mean is that there are, of course, the whole business started with like the unders localization and the many-body localization into many-body physics. Already these two concepts are a little bit different in many-body physics, and then there is also the localization if you don't have randomness, let's say, or a special type of randomness or quasi-periodicity. Then you have another type of localization, and also in the quantum walk literature, they try to find these analogs of these things. But what I'm asking is like, are these analogies like completely parallel or not completely parallel?
Well, to be honest, I don't know if they are completely parallel, because in Anderson's case, we have an analytic solution for the asymptotic limit. I mean, we know that the system behaves in that way when time goes infinity. But in our system, actually, these calculations are all numeric, to be honest, and we don't claim more than that. So I don't know how this system behaves in the asymptotic limit. But we have some strong evidence that all the eigenstates are localized after I don't know, maybe 10,000 steps. Also, I mean, as I showed you in this here, I mean, this is a very robust graph. I mean, it doesn't change after a couple of steps, after some number of spins in the position.
I see.
Yeah, but our calculations are fully numerical. We have no analytical solutions for this. So I don't know how our work is comparable with this Anderson's.
Well, not Anderson. I meant this
at least in this
translation invariant.
asymptotic limit.
Yeah. Oh, okay. Thanks. I mean, this picture is of course very nice and suggestive on what happens. Okay. So people are also asking for all the references of your presentation, but that discussion is typically going on Discord, and there are many comments.
I can.
On Discord. And like a final question before you go, and do you plan to go on with some ideas concerning this translation invariant localization, or what are you planning to do around this, or this is like finished, or it's secret? I mean, there can be many options here.
No, actually, this is finished. Probably none of us will will consider any extension of this work, because it took quite a long time for us to complete this work, at least for 4 years. And actually, the article is full of a lot of ideas. I try to summarize this. It's a very long paper. I mean, we consider a lot of things, even many-body localization and some indications, because you know, quantum Walker actually here acts as a mediator of interaction between this.
Exactly.
So we also made some calculations for this many-body localization for the spin chain. But I completely omit that part in my talk. There could be some interesting extensions of this work, but I don't think none of us will be interested in this anymore.
These are two questions. I find one very interesting. Okay, let's read the other one, because that question is maybe simple, or I don't know, that's from Discord. Thanks, Adam, for posting it here. Can you please explain what you mean by spread of classical/quantum walk? But I mean, I guess this dynamic.
Spread of, I mean, it's the variance. I mean, it's the variance of the. For example, it was here, but I was simplifying the slides. I just deleted it. I mean, this is a nice measure which reflects the spread of the quantum walk. Actually, how probability distribution here is spread along the origin and in the vicinity of the origin, let's say, around the origin. Sorry. So that's what I mean by spread. I mean, we start with a localized state at a given site. So it spreads along the lattice in time. That's what I mean by spread. So variance is a nice measure of it.
Sure, absolutely. I mean, yeah. So then from Akash, could you please say something about how the decoherence of spin affect the interaction with quantum walks? I guess like how the interaction with quantum walks result in a decoherence of the spins, right? That's what.
Well, we didn't study decoherence in this paper.
Yeah, but what I think what Akash wanted to ask was like since that it acts as a mediator, right, between these spins, it also gets entangled with them.
The interaction parameter entangles the position.
Exactly.
Yes. But it's just a coherent interaction between the position space and the.
Yeah, but I guess what Akash meant here is that if you look at only one like the positions or the other, like how those are entangled. But I guess okay, so you didn't particularly consider that. I mean, this can be like one can be seen as an environment in this.
If you trace out, for example,
if you trace out exactly
spin degree, spin chain degree of freedom, then how it acts like a decoherence for the system. Well, I don't know. I mean, we didn't consider it. I mean, we considered this as a just it coherently evolves in time, and we didn't consider any decoherence effect or something like that. So I better not to talk about it because I don't know.
You're running out of time, and suddenly these questions pop up in the beginning. Not so now. Adam asked a nice question, but this is going to be the last question. Some time ago, I was working on designing quantum walk evolution, continuous time, quantum walk evolution, which is well defined for general directed graphs and reaches a ballistic propagation. Is there an example of such in discrete quantum walks? Well, yeah, it reaches a ballistic evolution. I mean, and also that it's like somehow has a compatible with the directed graph structure. So, for example, if you have it spreads along the direction, sort of.
I think there are a lot of studies for discrete time quantum walks on directed graphs, but to be honest, I haven't studied any of it.
Okay.
I have no knowledge, so it's better for me not to comment on it. But I'm almost sure there are at least a couple of studies in the literature which considers discrete time quantum walks in directed graphs. But I don't know whether they spread ballistically or diffusively or how they spread. To be honest, I have no idea.
Yeah. Okay. Thanks a lot. So basically, also Akash says thanks for answering the question. So thanks a lot, and we are done with this very nice presentation. Thank you very much.
Thank you too. Thank you, Sultan.